Sorry, the video stopped. My hand incorrectly. My thumb just pressed upon the back button, which if I stopped, I apologize. So I'm just carrying on from the same place where I finished. Where the video cut off unforeseenly. 6. IT, so that's 65 times 12. That'll be 7. Cubed of chlorine gas. Yeah, because the oxidation number is 1, so chlorine's oxidation number is 1. That'll be 96.4 cm cubed. Quite a lot. It's just around about 1 litre. Quite a lot of chlorine shall be. So it's a bit. It's only 1.24 grams of calcium, whereas 7.46 grams. And you can see that, because for every 1 mole of calcium there are 2 moles of chloride being released. So whatever molarity this was, it'll be double the molarity, and hence double the relative atomic mass in ton. So yeah. So the answer would be 0.24 grams of calcium, and then either this or this, because the examiner didn't specify whether it was at RTP or STP. I'd give them both the answers. So 7.46 and 6.696. So 746 cm cubed and 696 cm cubed. The next question is a current of electricity liberated (6.22 millimole of silver. That comes out to be grams of silver, and it was from the electrolysis of silver nitrate solution. That's what needs to be specified. What mass in grams of aluminium would be liberated from a suitable aluminium compound using the same quantity of electricity? So here we can understand so in this equation of mass deposited, we know this, and we know this, and we know this, and we know this. So this doesn't matter, and this wouldn't matter either because it would get cancelled out because it's equal on both sides. So what we've got here is this and this and this. So we'll have to use equivalency, unitary equivalency. That is of silver times Z of silver divided by A of silver. Aluminium, Z of aluminium, So we'll have to use this equation just like we use C1V1 over N1 equals C2V2 over N2. So it'll be 0.672 grams times 1 divided by 108 grams per mole. And then we have, we don't know this for aluminium, times oxidation number, which is +3, and then the AR is 27, so 1/9. So that'll be, just multiply this by 9. So we get, okay, that's what we get. This is the amount of aluminium that will be deposited in the same situational scenario with the same current, same time, and the Faraday constant and the rest. So of aluminium The next question is slightly longer. Don't vomit. That would just suggests that you need to read it carefully, and the rest is in your hands. You can conquer it if you read it carefully. So the time is 45 minutes, 60 seconds per minute. 2,700 seconds, that is. Then we've got the mass deposited. Ooh, 0.203 grams of silver and silver. So this is a series circuit, and in series it'll be, current will be constant, it will not change, but the voltage will continue to break. You might remember the question we did earlier, and in the previous video, the previous video of part 1 of 2. So it's got 3 cells. What cell 1 is to do with silver, cell 2 is to do with hydrogen, cell 3 is to do with lead deposition. So this is lead deposition. So cell 1 silver, cell 2 hydrogen being evolved, and cell 3 is lead deposition. And this is from a solution of lead nitrate. Solution of lead nitrate, I'm going to put aqueous, and when I put aqueous it means a solution. The second one will be H2SO4, aqueous, is it? Yes. And the first cell is silver nitrate, as it's very typical. Silver nitrate solution. So just draw a boundary here. So this is in series, which means current remains constant, but it's the voltage breaking every single time. So one calculation of current shall suffice. So we want to find out the current passed, the volume of hydrogen collected at this pressure, and in 18 degrees, and the mass of lead deposited. So the current passed will be I'm going to start off with silver. Any answer in one stage without so we're finding this, so it'll be current will be this, the mass deposited is 0.203. I should have written it down, but I wrote it so you would so it would be 0.203 grams times 965 times 1 divided by 27. That'll be 67.2 milliamps. Got it. So we've found the current now. I'm going to keep it here for future reference. Well, we'll just write it down here. Bear with me, please. So time is 45 minutes. So time is current is IT, Q, and what else? Yeah, that's pretty much it. Now the so we found that. Now we need to find out the volume of hydrogen collected at this much pressure. It's a bit tricky. We'll have to use volume of oxygen. Hang on, I think we need to first convert newtons per meter square, pascals to decimeter. That would have been the shorter, quicker way, but because I can't do it and I'm in an exam situation, I'll have to find out, I'll have to see what I can make of my resources. So I'll have to use IT over F because it seems like a very low temperature, 18 degrees. It's 291 kelvins, and that's room temperature, I think. That's room temperature pressure. Or maybe it's STP. It seems like STP. So, now that'll be... The answer to that would be... Now this wouldn't, and this will become oxygen and water. This would become hydrogen. Just talking about this. So two moles of water, 1 mole of oxygen. So 1 mole of oxygen, 1 mole of this would give 2 moles of oxygen. So the answer to this would be... I'm going to find out the answer and write it over here. And that'll be... dm cubed, or it would be 10.5 centimeters cubed. Oxygen gas. Now I'd like to use PV equals nRT and see what I can come up with, because I know this and this I know, this I know, this I've got, so but for me to be able to verify the volume here, I need to know the moles of sulfuric acid, the solution of dilute sulfuric. I need to know what mole, because I know this, I can't verify the volume. So 0.0678 times 2700 second times 11 point. That's not dm cubed, I apologize. That's just 11.2. My oxidation number. So that comes out to be answer. If this was the number of moles of oxygen would be So this means this much was liberated from 1 mole of 4 moles of this liberated this. So 1 mole was 1 mole is 3.7 10 to the power minus 5. So this must be 4 times that. And if this is 4 times that, that's 1 more. That'll be 1 mole. So this is how many moles of sulfuric acid were there. Assuming in 1 dm cubed, I guess. So this is 1 point per dm cubed. We're assuming per dm cubed because we've taken this in dm cubed, and this is in Kelvin, and that's in so it has to be in dm cubed. The 1 mole of oxygen is liberated from 4 moles of hydroxyl ions, and 1 mole of hydroxyl ion comes from 1 mole of liquid sulfuric acid. So yeah, that would be that if the number of moles of oxygen is 3.676 times 10 to the power minus 5 moles, it would be the number of moles of sulfuric acid per dm cubed would be 4 times of this. That'll be 1.5 times 10 to the power minus 4 moles of sulfuric acid per dm cubed. That's the only way I can verify it. The examiner hasn't given me, so I needed to. This question seems very, very old, probably from the 70s, which is why they didn't specify whether it was STP or RTP. But in modern questions, you'd get a clear indication of STP versus RTP, which is when, if it's STP, you can use 11.4 here, and when it's an RTP, room temperature pressure, you can use 12. So now I found out the mole of oxygen released. Now, after which I need to find out the mass of lead deposited. The mass of lead deposited will be so 0.2 grams of lead achieved its elemental form. After the electrolysis. So long question indeed, ever so confusing. But if you look at this equation, equation number, so we take it as volume generated. And we look at PV equals nRT. We look at, we substitute for V, and that'll be nRT over P. So if we equate these two, it'll be N RT over P equals IT 11.2 over 2F. So I had this, and this. I didn't have that. And 1, 2, 3, 4, I had all of it. So number of moles. So now, I mean, can I do that now? Hang on. Let me write this equation down. It's very useful. So nRT over P equals IT over F times 12 or 11.2 over, yeah, why 2F? I mean, the reason I'm writing 2F is because of the oxidation number. So Z, I'm just going to put Z here. So that'll be, we have to find out the moles first. So the, let me do that again. So I have to find for moles. So I'll have to do I'm just using 11.2 by approximation because I think it's STP, not RTP. So we all know what F is. T is temperature, R is 8.31, 2 is the oxidation number of oxygen, 11.2 represents STP, time, current, and pressure. So joules per kg per Kelvin, something like that, and then coulombs per mole. Number of moles of oxygen. Sorry, I shouldn't have given it this kink. This represents the Stokes law. It's something else. So that's just, yeah. So anyway, let me find out the number of moles. Sorry, there's a Z there as well. And there's a Z. I got 0.2 moles of oxygen. That would be 4.5 dm cubed, 4.8 dm cubed of of oxygen. Around about 4,779 cubed. Yeah, for that mass I should be getting this much. So this answer for 11.2 dm cube, and then yeah, that was incorrect. So this one seems a bit incorrect. This one seems correct. Okay, so I'm going to do the next question. So sorry, I don't know where they got cut off. The answer to silver question, so the question silver question number 9 was, if a current of 0.1 amp had been supplied from an infinite source of silver, how long would it take for 1 kg's worth of silver to be electroplated or deposited onto the cathode? So I used this equation, flipped it for time, and found out that it'll be 8,935,185.19 seconds, or 148,919.7531 minutes, or 2,481.996 hours. So I found that by flipping it for time, and now I moved on to the question number. I moved on to question number 12, the last question, which is, in the electrolysis of a solution of potassium chloride, 100 centimeter cubes of chlorine is produced at 20 degrees Celsius, which is 293 kelvins, at a pressure of 9.9 times 10 to the power 4 newtons per meter squared. How many seconds has a current of 0.75 amperes been flowing through the solution to effect this? So I found out that we'll have to first find out the number of moles of 100 centimeter cubed worth of, which is 0.1 dm cubed worth of chlorine gas. So that'll be the number of moles Yeah, it seems like room temperature, so I'm going to use 24. And that'll be 4.2 millimoles. Now that I've got that, I'm going to juxtapose it, add it here. And then find out the time. Now the equation for time in this case would be ZNRT divided by, that's the T for temperature, divided by IP12 equals T. And that would become minus 1 times 4.2 millimoles times 8.31 times 293 kelvins. One, two, three, four, divided by current would be, the current in this case is 0.75 times pressure is 9.9 times 10 to the power 4 Pascal times 12, which signifies room temperature pressure. The time would be it's quite a small amount of time, and it's not correct. So the pressure we've got the volume here. There was no need for this amount. We could have just done, hang on, I'll just now try doing it without the molar. So we'll do V equals chlorine, is it? Yes, so that'll be just one. Right, so that will be so that'll be this, and and now I've got the correct answer, which is good, that's nice. 10,722 seconds, which is close enough. Well, now it's like 10 times bigger than 1,050 seconds. Hang on. V equals IC divided by F times 12 over Z seems to be breaking apart here. It doesn't seem to be working very well. It's giving answers that are slight orders of magnitude larger than what's mentioned in the book. So CM cubed times F times Z. I think the Z should be divided by 12. So times 0.75 IT, yes. V over I times 12 times FZ. "78 minutes, around about 3 hours. around about 3 hours. So it's been quite challenging, very nice, very thorough in terms of its rigor. It can be very difficult, which is why it's often ignored. Students don't want to attempt these questions. The last 3 questions I'm going to attempt. The first of them is a current of 0.2 amperes. It's passing for 18,000 seconds. And mass deposited of gold with an oxidation number of 3 is 2.45 grams. How do we find out the charge? Not yet, so we have to find the charge. The charge will be then I'll skip the numeric part and get to no, I can't skip the numeric part actually. I'd like to show every single step. Great, got it. So the oxidation number would be 3 for gold, which it always is. It's trivalent, but it's highly inactive and it's inert. And the penultimate question would be the mass of lead deposited at a cathode by current 0.15 amps flowing for 3 hours through a solution of lead 2 nitrate is given. How much would it be? So the mass deposited that'll be, baby, please. Okay. elemental lead. Lead elemental, lead proper. The last question is the current of 0.1 amps for 3 hours passing through a solution of dilute sulfuric acid. How much volume of oxygen gas in dm cubed at STP would evolve at the anode? So it'll be volume of oxygen equals 0.1 times STP, so that'll be 11.2 divided by 2 . Nine and 26, 6 times 12. Oh boy. Double check. Question number 3. Section 1, question number 3. B, so it would be B, but Y? And then the answer for B would be, if you resolve B, it would come out to be 0.1 times yeah, the number of moles of oxygen are 4. So it'll be 63 centimeters cm cubed, round about 63. So you have to take, so volume of a gas released is the current times time over number of moles of electrons times F times STP or RTP. And we know that 1 mole of oxygen releases 4 moles of electrons. So in addition to this formula, which is giving us very, very large answers, we have to learn to use this formula, which is far more succinct. I mean, there's no deficiency of succinctness with this one, but for this, you have to realize that when you add the number of moles of electrons, it makes it far more specific. So, and 12 or 11.2 is a crude approximation, which is why the volumes are aggressively approximated as well. So let me just repeat the volume for any gas released at any electrode. It'll be volume of any gas released at any electrode equals times current times time in seconds, divided by number of moles of electrons times Faraday constant times STP or RTP. So that's that. And although we can see some similarities between these two formulae, QOF times 12 or 11.2 divided by the oxidation number. But it is a reality that in philosophically speaking, you can't really, the philosophy is that the oxidation number is more applicable to metals at cathodes than it is to gases. For gases, it's the number of moles of electrons that matters. So this formula will be far more correct than the other one. So I'll have to go with this one. So this formula is far better than this one. This is this template is more useful for metals. So I think we learned quite a lot. 2 of our questions were incorrect, and 2 were hyperinflated. But we learned, we went through every equation systematically. Every question was approached quite, you can say, systematically or in an organized fashion, and we were able to get the correct answer every single time except for twice. And once we used the correct formula, the incorrect answers turned to correct ones. So that concludes my work on electrochemistry, advanced electrochemistry, and I hope you must have learned something from it. And yeah, I'll take it from here. And if you've got any questions or comments, and please post them in the section down below, and I'll take it from here. Thank you very much. And again, let's revise the formula one more time. This is where we started from, and take a screenshot of it. I want you to take a screenshot. Please take a screenshot. 5, 4, 3, 2, 1. And take a screenshot of this as well. 5, 4, 3, 2, 1. And cut off the oxygen part. And that's that. So, we haven't done the electrochemical cell calculations, but everything except which students avoid. So we've tackled the most difficult part of electrochemistry, and we've learned from our mistakes, and we've also realized where and how and why hyperinflated answers might come about, and what are the causative agents for hyperinflated answers. We also learned that if you aren't attentive, you can make mistakes during the use of your calculator and ruin the quality of your answer and lose those essential marks, which is why sleep before your exam is very, very important. You have to have complete sleep before you approach your examination. Working the whole night, revising, trying to cram in night prior is not very smart. It's quite damaging. And believe you me, even if you're underprepared and you have a full night's sleep, you go in there calm with a hot drink and banana breakfast, you'll be able to perform quite well. And one of the most important ideas of approaching these large, difficult questions is to not have a sense of guilt, and do not vomit when you see these large, difficult questions. So when you come across these questions, this one that was correct. I was told correctly, and this one, this. When you come across them, I remember this one. So always, never vomit, and be organized and tabulate the data. And make sure you've tabulated the data, and then you approach the question. So as you may have noticed, I was tabulating the values prior, and then it was very easy for me to find out the unknown and then substitute the equation for the unknown and get the correct answer every single time. So these are some of the virtues that will help you gain superior grades at professional or degree level exams, and that concludes my work on electrochemistry for post 16 curriculum. I'll do a video on nuclear power plants in future, but for now I'll be signing off, and this is probably my last video till I can sort my affairs out and get back in action, and then I'll be able to post some videos about NPP generators. Thank you very much. Take care. Bye now.